Hi, I'm Umang, and I'm part of the Armstrong Group in the Department of Chemistry and Biochemistry. I'll be presenting on the usage of teicoplanin and A-glycone for the pre-concentration of D-amino acids and D-amino acid-containing peptides. D-amino acids have been thought as biologically irrelevant compared to L-amino acids. However, recent studies have shown that there are elevated levels of D-amino acids in skin cancer cells. Another example of the presence of D-amino acid is presence at specific locations within the beta amyloid peptides extracted from patients with Alzheimer's disease. D-amino acids and D-amino acid containing peptides have a low concentration compared to their L counterparts. This is the reason why we do pre-concentration for analysis. With any chromatographic separation, there is a stationary phase and a mobile phase. Compounds are separated based on their affinity to the stationary phase or the mobile phases. A column is packed with the stationary phase, and the mobile phase along with the analyte is passed through the column to achieve separation. The stationary phase that we will use in this project is teicoplanin and A-glycone, also known as TAG. Structure is shown in figure 1 over here. TAG has a strong retention of D-amino acids and D-amino acid containing peptides with the condition that the D-amino acid on the peptide needs to be on the C-terminus. This is why we can use carboxypeptidase Y, which is an enzyme that hydrolyzes peptides from the C-terminus as shown in figure 2. You can see that it cleaves the peptide bond and releases an amino acid. The C-terminus here is the carboxylic group and the N-terminus is the amine group. To our benefit, D-amino acids are resistant to hydrolysis by CPY. So the overall objective is to hydrolyze the amino acid containing peptides while the D-amino acid containing peptides remain intact, and it helps us to isolate and analyze it using TAG. The instruments used in this project, along with the column dimensions and the chromatographic conditions, are listed over here. I'm going to talk a little bit about some previous work done on this project. In figures 3, we can see the separation of dipeptides. In the figure, the absorbance is plotted on the y-axis and time is plotted in the x-axis in minutes. And all the dipeptides that are listed here, glycine is the first amino acid and the second amino acids are listed here. Only the second amino acid have either a D or an L configuration. As seen in this figure, peptides with an L amino acid at the C-terminus elute faster than the ones with the D amino acid in the C-terminus, and all the ones with D amino acid in the C-terminus elute sometime after 40 minutes in this case. Figure 4 shows the retention curve of a tetrapeptide with only the last amino acid being either D or L. In the y-axis, the retention factor is plotted, and on the x-axis, the percent methanol is plotted. The retention factor as shown here is the difference of the retention time of the analyte, which is the total time spent by the analyte in the system, minus the dead time, which is the time the mole phase spends in the column, and all of this is divided by the dead time. It was found that 80-20 methanol water had the most optimal separation as it gave the highest retention factors. We have a typical U-shaped curve here with the peptides having high retention factors at high water concentrations as well as high methanol concentrations. In figure 5, the delta K is plotted against percent methanol. Delta K is the difference in the retention factor of the D amino acid minus the retention factor of the L amino acid. As you can see, as we increase the percent methanol in the mobile phase, the change in retention factor increases, which means that the amino acids are better separated. We found that 90-10 methanol water was the optimal concentration for these separations. In figure 6, we have this enantiomeric separation of amino acids at 90-10 methanol water concentrations. In the previous method, I was not able to see basic and acidic amino acids, and what's different in this method is we used a lower pH, so it's a pH of 3.0, and you can see that most amino acids are well separated, and especially the acidic amino acids were better separated compared to the previous method. So in conclusion, 90-10 methanol water as a mobile phase provided the optimal results. For future work, I need to optimize separation of basic amino acids, which are not listed in figure 6. Likewise, we have to ultimately evaluate the feasibility of using TAG in a solid phase extraction cartridge to separate L amino acids from D amino acid and D amino acid containing peptides. To end, I would like to thank Discover, Sepulco, the Watch Foundation, and ASAP. Thank you for listening.